Hello students, myself Muturaju NP, working as assistant professor in the Department of Mechanical Engineering at Vidyavardhaka College of Engineering, Mysuru. Now I will explain you people about the Euler's energy equation for turbo machine, and also this will be includes the alternate form of Euler's energy equation. You know that what do you mean by the turbo machine and its relation? All these things you have studied in last video only. That will be given with the flow F is equal to d of mv. The what is the mv means momentum by dt, that is rate of change of momentum with respect to the time. That will be gives what your force. So mass flow rate will be given like this. Newton's first law of motion, second law of motion, here you will get the equation like this. The change in tangential velocity of the fluid particle from inlet to the outlet, we are doing this one with respect to the turbine. See, the VU1 is greater than the VU2 means it is a turbine only. So VU1 is greater than VU2, and then mass flow rate multiplied divided by time, and then GC. Most of the time students have in the confusion that what do you mean by the GC, that don't bother about the GC and all. When this turbo machine subject evolved, and then that time the subject was the written in terms of CPS, FPS units, CGS and FPS units. That time the conversion, during conversion unit conversion, the GCs remained as it is. So we kept like that only. They have kept in the you just write GC, that's all. So mass flow rate of the fluid, per time into VU1 minus VU2, V into R will gives the torque. So this M divided by T, VU1 into R1 minus VU2 into R2. So this is the, will gives the what torque to you guys. Now energy developed per unit mass flow rate, M, that's why the torque divided by mass flow rate will gives the energy, like that you just observe. And also you must multiply this one with the omega, then omega into R1, omega into R2 you will get. So omega into R, you will get the what, U, blade speed velocity, that is a linear velocity. If the blade is rotating at a particular RPM omega speed n, and then omega is angular velocity, then linear speed of the blade will be is equal to U. Therefore VU1 U1 minus VU2 U2, this is the Euler energy equation. Let us go for the alternate form. Whenever it is asked for the alternate form, you must write the velocity triangle, this one. As usual, you know, this is VU1 total, this is U1, and then alpha 1, all these things you know very well. Now we have to go for the this one VF1 square we want to take in two velocity triangle. This is one velocity triangle, this is fully, it will be another velocity triangle. Here you take VF1 directly. So VF1 square, V1 square is equal to VU1 square plus VF1 square, but VF1 square you can write V1 square minus VU1 square. Next VR1 square, it is equal to VU1 minus U1 plus VF1 whole square. But VF1 square you alterate this equation, then you will get this one, and then expand this one properly, that is A minus B whole square formula, VU1 square plus U1 square minus 2VU1 U1, then multiply negative inside, and then you will get this equation. You call this equation number 3. Compare equation 2 and 3, you will get this equation. V1 square minus VU1 square is equal to VR1 minus VU1 square minus U1 square plus 2UV1. So this will be the thing. So VU1 are the common here. This will be get cancelled. Therefore you will remain with the V2 VU1 U1 is equal to V1 square plus U1 square. This one comes this side, that will be plus minus VR1 square. Therefore VU1 U1 is equal to V1 square plus U1 square minus VR1 square. Similarly VU2 U2, okay, this one will comes, and then put VU1 U1 and VU2 U2 in the equation number 1. That is, you will get this equation. So rearrange this all the things. 2GC, rearrange V1 square minus V2 square, U1 square minus U2 square, plus VR2 square plus VR2 square minus VR1 square. So divided by 2GC is the common. Now the D is the dynamic enthalpy I will consider. Already I told you people that dynamic enthalpy will be pertaining with the what? Absolute velocity, change in the absolute velocity of the fluid, that is changing by kinetic energy from V1 to V2. Therefore static enthalpy is U1 square minus U2 square plus VR2 square minus VR2 square. See, these are pertaining to the turbine. This is absolute to the your turbine. This is absolute to the turbine, out of the turbine, inlet and outlet. But here it will be involved in the turbine only. U1 is the blade speed, U2 is also blade speed, VR2 and VR1, these are the relative velocities which having turbine blade speed as well the this one dynamic, that will be absolute velocities. This I explained. Okay, therefore let us go for the new definition. Very very important definition in your turbo machine is that degree of reaction. What do you mean by the degree of reaction? That mathematically it will be expressed, it is the ratio of static energy, change of the static energy to the total energy. What is the static energy? S, and then I will designate it with the S, and then total energy dynamic plus static. Therefore this will be the equation. See, this is the turbine blade. To make you people a better understanding, you are a better understanding, I am showing this one. When the fluid come out of the turbine, after it is while it is rotating, the enthalpy of the fluid, energy of the fluid will changes continuously over the blade. See, it will changes continuously over the blade. During this time what will happen? Pressure, volume and its energy will be changes on the turbine. If you consider pressure, volume and all the things, thermodynamically also it will get changed, and also by according to a Bernoulli's equation also the fluid energy will be continuously change over this one. That will be static enthalpy. Whatever the energy it will be change on the turbine blades, that will be static energy, change in the static energy. But dynamic enthalpy is absolute, that is V1, see V1 and V2. This is the turbine, right? Fluid will be expand. Okay, absolute V1 and V2. That's how you want to understand. Okay, static enthalpy means continuously changing of the fluid energy over the turbine blades. When fluid energy change over the turbine blade, it will start to rotate. Okay, it will give its energy to the turbine. Next, this is the degree of reaction equation. U1 square minus U2 square, VR2 square minus VR1 square. This is the static, and then this is the dynamic. Okay, next, utilization factor. It is the ratio of total energy to the maximum energy can be utilized. What do you mean by the maximum energy can be utilized? That means the loss at the exit should be very very low. Which is the loss at the exit? That is your velocity, absolute velocity at the exit, that should be very very less. That means here for maximum utilization factor that will be 0. So, and also another concept I want to tell you, if fluid absolute velocity at exit of the turbine is 0, then fluid won't come outside. That's why there should be minimum amount of the velocity should be there with the fluid, that is V2 should be there. That should be very very minimum, then only you will achieve the maximum utilization factor. And also see this equation, I will write this one as the E, total energy. Okay, I will write E plus V2 square divided by 2. See, please keep in your mind, this is very very important equation while deriving the another equations. Next, deriving the other equations, also to solve the problems, sometime you can use this one equation directly, you will get the answers. Okay, see, put E here and VT square divided by 2, then you will get this one. So this is correct, that is E is equal to E divided by E plus VT square divided by 2. Next we can go for maximum utilization factor. Very important concept of the maximum utilization factor. You see here in this equation, last equation, you see in this equation what you have seen. See, in this equation your V2 is very less. Okay, if V2 is very less, then this will be the maximum. Are you getting my point? V2 is very less, then maximum utilization factor will be there. See, you can't do this one. See, this, except this one, nothing can be changed. Okay, V2 should be very less. Keep in your mind, please observe here, it should be very less. When the denominator, this one will be less, this term will be more, and then this term will be as it is constant, and then your value will increases. Therefore V2 is very less. Your, as usual, exit velocity triangle you write, but in the exit velocity triangle V2 can't be coincide with this one. Okay, therefore V2 will be coincide with the flow velocity at the exit, which will be written perpendicular to the blade velocity. Then it will be coincide with the fluid velocity. Therefore the exit of the fluid turbine will be axial. That axial exit, they will say that axial exit. Therefore fluid will be exit axially parallel to axis of the turbine. Therefore your velocity turning turbine will be turned like this: VR2, then V2 and VF2, that is axial, it will be coincide with the axial velocity, and then VU2 will be 0. Keep in your mind, exit at the exit, already we have derived the equation VU1 U1 minus VU2 U2. In that VU2 U2 is 0, nothing will happen to the equation, it will be positive only. Therefore your VU2 will become 0. When VU2 will become 0, the turbine efficiency will be maximum. Thank you one and all.